So here's a few news links. This one, Twitter, as I'm sure we all know, is worried about spreading misinformation. So what they are going to do is turn on something called Birdwatch, which is a community-driven content moderation platform. And the thing that I notice about this is exactly what Parler used. If you listen to Kara Swisher's podcast, Sway, which I highly recommend, she had the guy who runs Parler on there, and he explained how his system works, and it works like this. So several other users moderate things, and it doesn't work at all. And as you see, Parler got shut down. So I'm not sure how much good this is going to do, especially in the current situation when the main issue is that people don't agree on what the truth is. So if you post something left-wing, all the right-wingers will scream and say that's no good. If you post something right-wing, all the left-wingers will scream and say that's no good. So just having like 10 votes that something is no good doesn't really get to the point at all. So anyway, they're going to launch this Birdwatch. Every platform is trying to solve their problem this way. Just a sec, I'm going to try and improve my background here. I need to move this and this. All right. There, the perils of amateur theater. Anyway, so Twitter is trying to do that. We'll see. This one I was real glad to see. Moderna is making a booster shot because one of the new mutants of COVID-19 appears in early results to be resistant to the current vaccine. So that's revolting. All of us are waiting forever for the vaccine to come out, and then it's not even going to work. So anyway, they're going to have some kind of booster shot, which will help protect you from the variants. And I sure hope that works. Maybe we're going to have to get a shot every year or a shot every 2 years or a booster shot every now and then or something. But anyway, at least they have some plan to deal with it. So Microsoft Edge is going to use homomorphic encryption. I'm going to start the exploit development class in 7 minutes. So I just talk about the news in the first few minutes of each class, that's all. So Microsoft Edge is going to use homomorphic encryption to check your credentials against a list of compromised credentials. And homomorphic encryption is a very new kind of encryption where you can encrypt data and then you can do some mathematical operations on the data without decrypting it. And so the idea is you could encrypt a password, send something encrypted up to a server, and find out whether your password is on that list or not without exposing the password. This is one of the old jokes. Still showing Twitter tab. Oh, it's not showing all the tabs. Thank you for telling me. Let me see if I can figure out how to trick Zoom into showing the right. Ah, yes, it is, isn't it? And I closed that tab. All right. Let me see if I can figure out how to get Zoom to share the right thing. One thing would be to close all other browser tabs. All right, let's see what this does. Share screen, Brave browser. Yes. Aha, looks like maybe this is going to do it. Yes, this is going to do it. Okay, good. Thank you for telling me. So that's the idea here. You can have a homomorphic encryption. The one problem with homomorphic encryption is that it's 1,000 times slower than the normal encryption. But the way Microsoft is employing it, it's only encrypting something really small, like your password. And it looks to me like it's doing all the calculations up on a server instead of on your client. So anyway, this is the first practical application I've seen of this homomorphic encryption stuff. It may be growing. Many people are developing versions of it and pushing it out. We'll be hearing a lot more about it. I included a few examples of it in my encryption class last semester, but the early versions of it we used were mostly notable in how incredibly slow and impractical they were. This is apparently a known vulnerability for years. If you have a Linux desktop, all you have to do is plug in an external monitor with a USB cord and unplug it a few times, and it will let you past the lock screen. And apparently people have known this for 15 years. So that's pretty awful. maybe they'll finally do something about it now that it's becoming more commonly known. So Microsoft, Bill Gates, Microsoft was nearly broken up. Back because of Windows 98, around the year 2000 or so, there was a big lawsuit to break up Microsoft. And when it was over, they asked Bill Gates, what have you learned? And he said, I've learned that you have to donate to political campaigns. And the new president of Microsoft gave a talk, and minutes of that talk leaked out saying what he said is, this is how it works. They say, yes, I am aware that we were donating to politicians that are doing terrible things contrary to our values. We always donate to all the politicians of every party with complete disregard for their values, because that's what you have to do in America. If you want to stay in business, you have to basically bribe every politician. If you don't, then whoever wins the election won't take your phone calls, and you won't be able to get anybody to listen to you, and they'll just pass some law that totally destroys your business. So it's just the cost of doing business that you have to donate to these political action committees. And so Microsoft is trying to propose, some of the Microsoft workers are hoping they'll be more altruistic and idealistic and lobby for democracy and only support politicians with the values they agree in. And we'll see how that turns out. But this is, I think, coming into the open more and more. America has a corrupt system where you have to bribe politicians just to survive. And that's what Bernie Sanders has been saying all along. But getting the money out of politics is not simple, because all the politicians with all the power are sitting on a pile of that corporate money, and changing the system will undermine all the existing power structures. So of course they will block it. So I don't know how we're going to fix it, but at least it's sort of nice to see the truth coming out. So this thing here is, this Deviant Ollam is a great guy. He wrote books about lockpicking and does physical pen testing. And you can buy this thing like a space helmet, which you can wear on an airplane. And it has a motor and it filters the air, so you don't have to wear a mask. And people can see you, but you're protected from COVID. So he says it looks good, but he said it's actually pretty uncomfortable and nasty. And this particular product is not worth it. But I think there'd be a market for a better version of that product. So this is an interesting issue of open source intelligence, which is a big issue. So this guy was at the Trump riots, and he took pictures of himself. And so this just shows how you track people down with open source intelligence. They took pictures of him doing stuff like beating somebody or something at the riot. So they showed how she tracked him down. He's easy to find. He posts on Telegram with a name similar to the name that he used up here. And he had a name Jonathan Gennaro. So she just tried various versions until she found someone in the right age range. And then she found a picture to know that's him. Then she found him traveling, and you found out where he's wearing a t-shirt for a campaign of Virginia politicians. So that means he was a resident of Virginia at that time. Then she found a tattoo that shows in memory of someone, I'll see you soon, bro. So that means he had a brother with that name. So, this is how you do it. A lot of people in Anonymous got caught this way. They show how it works. They were able to find someone who died at the right age, and he was killed by a drunk driver and had a brother named Jonathan. Then she's able to find his court records. He was involved in a meth lab bust. So, they can pretty soon find out everything about you just from totally available public records. And a lot of people are doing this on sort of a vigilante basis. But I think what a lot of people don't understand is if you make a new account and go into some chat room and think nobody can find you, that's not very true at all. People can usually find you pretty fast, unless you're very careful. Anyway, I think we're up to the official time. So this is 127. So it's at samsclass.info. This is exploit development. And what we're going to do here is learn how exploits are made and developed. Now, the point of these is if you have a vulnerability in a system like a web server, that means somebody finds some way to do something unexpected on the web server. And what you usually do to find these is you run a fuzzer that sends random traffic to the server until it crashes. And when it crashes, you found a denial of service exploit. And after that, you would like to upgrade that exploit to a remote code execution exploit, where you can do arbitrary things more interesting than just crash the server. And that's what we're talking about here, is that process, how you move from a denial of service exploit up to a remote code execution exploit. And in almost all cases, you do it with memory corruption. The reason you crash it is because you managed to cause some object in memory to be misunderstood by the processor. And if you send it something careful, it gets misunderstood in a controlled way so that you're able to execute code on the server. So that's the point, and we'll talk about it and do in projects, do it for Windows and Linux. And we'll talk somewhat about Mac OS 10 and Android and ARM. But we're primarily going to spend our time doing Linux and Windows. So there are guest speakers coming on quite a few Mondays, the first Monday of every month. So the schedule includes room for them. On the guest speaker days, we'll just listen to the guest speaker. There won't be a normal class like this. I've got quite a few classes, and I lecture for about the first hour, and then I just answer questions. So if you want help, you can come to any of my classes. It doesn't have to be this class. Just come after about the first hour, and I'll be able to answer any questions about any topic. So let me see. Your point. You do not have to attend class. To get points, you just have to take the quizzes and turn in the projects. And I think there are some discussions to participate in too, but I'm not sure for this class. Anyway, there's a Canvas server that City College provides that you can use. That's where you turn in your homework, and where you take your quizzes. If you're not a City College student, I made a public server you can enroll in here to use. You won't get City College credit, but you can participate in the class and learn this stuff. So I think that's it for the basic introduction. And I'm going to just start with the first chapter. So I have to adjust my share. So I'm going to share the keynote there, and we'll see how well this works. All right. So just the first chapter in this book. This is one of the Bibles in this field. There are several books that are very, very famous, so they're worth using even though they might be pretty old. And this is pretty old, but it's still very important. It is a little bit dense and difficult, so I've written my own projects to make it a little easier, but it does have the information you need to know. So here's the basic concepts. A vulnerability is a flaw in the system that makes something unexpected happen, like denial of service or delegating up to administrator when you shouldn't be doing this. And an exploit is the activity that takes advantage of the vulnerability and does something. And typically you call it a proof of concept. If you're a bug bounty researcher or somebody finding vulnerabilities, you find a vulnerability, and then to demonstrate to the company or to anybody else that you've actually done it, you have to write code that will do something unexpected, like launch calculator or something. And that's called a proof of concept code. All right, so a 0-day is an exploit that has not been publicly disclosed, so there is no patch from the manufacturer, there's no known workaround, and so those are quite valuable. A 0-day, for example, for the iPhone that works without user interaction will sell for about $1 million, and it'll be held by people like the NSA and other nation states and used against their enemies until it gets burned. Every time you use it, you have a chance of getting caught. Your company might be smart enough to actually have defenses and actually stave a copy of the attack and reverse engineer it, and then it's no good anymore. So 0 days are only good until they get caught. Anyway, a fuzzer is how you usually find vulnerabilities in the first place. You just send a lot of unexpected input values into the system until you find one that causes it to crash. So we're going to talk about memory management. We're going to do 32-bit and 64-bit Intel systems and ARM systems, but primarily we're going to talk about Intel systems here. And so the point is all these work with memory corruption, almost everything we're going to do here. So you have to understand how data is stored in memory and how it's used in memory. That's one of the essential things you need. So we're going to talk about, now the fundamental reason that all these exploits work is that computers are stupid. They do not understand what they're doing. So what happens with computers is they store data and they do not know what that data is. That data could be instructions, it could be an image, it could be text, it could be anything. It uses the same kind of bytes for everything. So that is the fundamental problem. So you can put in something like it's supposed to be an address or a credit card number, and then you can try to execute it like code. And the computer is unable to know that it is in fact data stored for a different purpose. That is the fundamental vulnerability that we're going to exploit here. So when you launch a program, it creates a program address space, and there are different kinds of segments of memory. There's a text section, which is not contain any readable text. The name is misleading. This contains the program instructions, which are assembly language instructions in binary. Then there's data sections, which contains static data. And then there's the stack segments, uninitialized global variables, BSS. These both contain data, which might include readable strings. The stack is the main area that we're going to exploit. The simplest memory corruptions are stack overflow exploits, and that's where we're going to start, although we will proceed to other ones like heap overflow exploits. So the stack is designed for this subroutine process. This is something you see in all modern languages. In the early days, you would just write spaghetti code. I used to write a lot of this stuff back in the 70s in languages like Fortran. You would just run code and then you do a goto to go down here, and then you do a goto to come back, and you just have this snarled up mess where execution jumps all over the place. And the problem is you can't maintain that kind of code. As you try to add new features and fix bugs and expand it, you just lose control. So what's much better is to organize your code into little modules that do one simple thing, and then call them and do that one little thing. And so your main routine just calls one module to do one little activity and calls another module. And then you can update each little module and test them separately. So those are your subroutines. But this means you have to start with the operating system, double click something like Microsoft Word to launch it, then do something like do file open to open a Word document, then file print to print a document. And so you're running the operating system, which might be Windows, and then you're running Word, and then you're running a subroutine to print something all at the same time. So it's like a dream within a dream. You run a function, the function calls another function, that calls another function, and when you're done, it has to come back and pick up where it left off. And that is the process that the stack is designed to facilitate. This is why the stack has this strange property of last in, first out. You shove the data on the stack, and then when you call a subroutine, you shove more data on the stack with push that goes on top. And when you recover from that, you pop the stuff on the top frame off, leaving the bottom frame alone. So it's like a stack of trays in a cafeteria. You put them on, and when you pop them off, the last one on is the first one off. This is designed for the specific purpose of letting you have subroutines that call other subroutines that call other subroutines. And that is the primary activity that we are going to use to take over the machine. The heap is another data structure that is less organized than the stack. Instead of having this process where you put on a stack frame and another stack frame on top and another stack frame on top, and you always take the last one off first, it's just a bunch of data. You store data of different sizes just in chunks. And you can delete one chunk without deleting the other chunk. You can read them in any order and so on. So it's holds any temporary data that you would like to store for a while and then remove to clear up memory. So when your program launches, you'll see something like this. You'll have a text section that has the instructions, then you'll have a data section and the BSS, which is another data section. Then you have a heap full of unstructured chunks of data here. And then up here, you have a stack that grows down as you push and pop. And then you have kernel space somewhere. The kernel space is the high privilege address space of operations that have direct access to the hardware. Nothing you launch from your desktop by clicking on an icon running a program can ever directly touch the hardware. You're not authorized to. That's user land. If you want to touch the hardware, you have to ask a kernel routine to do it for you. And that's so you, anyway, that's a simple overview of program layout. And this entire class is going to consist of looking in more and more precise detail at exactly what happens in these memory regions so you understand how to exploit them. So I've got some Kahoots to look at. Let me bring them up and then share them. Here's my Kahoot. All right, and let me adjust my sharing to go here. Good. All right. So these are just quizzes. They're worth extra credit. You don't have to do them. But if you are one of the top 3, you will get some extra credit points here. And it just do this to stop people from falling asleep so much. So favorites, and this is 127, 1A, which is here. All right.
I don't see the Kahoot screen.
Well, I'm seeing it on my screen. You should see the screen of the.
I think you're only sharing the slide.
Oh, it's showing the wrong window. I think you were telling me. Okay.
Yeah.
Thank you. Good. I'm trying to improve my system and it's got a few defects. There we go. Thank you. Good. There. So go to kahoot.it and put in that number. Good. I appreciate the help. If something's wrong, please do that. Don't be shy. Come off mute and tell me. I see a question from Kara. We're just going through the first chapter. We went through the first bit of the first chapter. And I spend the first 10 minutes, the class starts 10 minutes after the hour. I spend the first 10 minutes just talking about the news. All right. Well, I got 34 students, so a few more might be coming in. I'll give it a few more seconds. All right, I guess not. All right. So what's an attack with no known defense? All right, that's a 0 day. Good. All right, how about the process of sending random data to a target? That's fuzzing. Good. All right, what section of memory is LIFO? All right, that's the stack, last in, first out. All right, so where are the machine language instructions? They're in the text section, strangely named. All right. And where's the read-only section? This one's a little hard. Okay, it's the text section, and we should talk about this. The text section, there is a rule in modern operating systems that you can have write or execute, but never both. So executable areas like the text section have to be, you are not allowed to write there, but you are allowed to execute it. So anyway, this question is a little misleading, and that's why these things are extra credit. They're not perfectly fair. But anyway, all right, so 3 for David. I hope there's only one David. 3 for Sean G. I think that looks like a good unique identifier. And I know who that is. Good. All right. Anyway, so we'll carry on. All right, let me go back to the slides, which will be here. All right, good. So let's talk about assembly language. If you already know assembly language, it's helpful. If not, we're going to review it in a simple way. I just warn you in advance, don't freak out. A lot of students freak out when they first see assembly language. They think it's hard. It doesn't have to be too hard. It's just a little strange at first. So 32-bit Intel is the most common assembly language, but there's 64-bit, and then there's ARM, and there are other machines around. But if you talk about the world of Intel, which is still the main one people are using, then it's 32 and 64-bit Intel, and the assembly language instructions are very much the same. We're going to talk about them both extensively in this class, and a little bit of ARM. So an instruction looks like this: move ECX 0x42. The 0x42 is an immediate number. That's 42 in hexadecimal. That's what the 0x means. So that's 4 times 16 plus 2. So that's 64 plus 2. That's 66. The move moves data from one location to another. So it takes the data, which is 66, and it puts it in this register called ECX. And the registers are just little areas of memory on the computer, on the processor. So this will move. Now this command, move ECX, is stored as a binary value. Everything is just a binary value in RAM, and that is this 1 byte. B9 is move ECX. So 42 is this. We're using a 32-bit processor. So when you have 42, it stores 42 and then 3 more bytes of data. So it really takes 4 bytes or 32 bits to store the value. So this is what that instruction looks like in memory. There's the command, there's the value. So 5 bytes are required to encode this one machine language instruction. And when it's executed, it takes the value 42 and puts it in the C register. All right, so then we can talk about Endianness. Well, yes, that's a very good question. Shouldn't it be the zeros on the left? That would be big endian. This is little endian. The little end comes first. So this is the backwards of the way you would normally write it for normal numbers. The least significant number is here, and this is more and more and more significant. Exactly the issue. Here's Endianness. This is the way we normally write numbers, where the most significant values are on the left and on the right. That's big endian, but Intel is little endian. So and that is going to give us no end of headaches all through the class. I don't know the reason for Endianness. I know for network packets, it has a small effect on efficiency. In IPv4 addresses, the first couple of bits transmitted of the address tell it what class it was in. So there was a time decades ago when switches and routers could run a little faster by putting the most important bits right at the start. These days, I don't think there's any good reason to have one Endianness over another. But it would have something to do with the actual layout of the transistors on the chip. Anyway, x86 programs are all little endian, and that is going to give us no end of irritation later. IP addresses are big endian, because as I mentioned, when you send an IP address over the network, the first byte has a special meaning. It tells it the class it was in back in the old days. Yeah, somebody has a nice link there to give more information about it. Anyway, so this really is the first byte of a network address, and you can't reverse the order of these bytes without fouling it up. So this really has to be sent that way. So it would be stored in RAM this way, but sent over the network that way. So we are going to have to consider endianness, and it's going to come back every now and then to be annoying. All right, then there's operands. The easiest thing is to spot is an immediate operand, just a number. Then there are registers. You can use them as number the source of data or the destination of data, and then there are memory addresses. So if you put EAX like this, then you're referring specifically to the EAX register. But if you put it in brackets, then it means take the value in EAX, interpret that as an address, and go find the RAM at that address. So this is indirect addressing or a pointer. There are various terms for this concept. So here's the registers in a 32-bit processor. x86, these are the registers you get. When I started, I used a 8-bit processor, and there was one register called A for the accumulator. And then they moved to 16 bits, and I think it was AX, and then there was 32 bits EAX, extended A extended. So there's A, B, C, and D. There are 4 general purpose registers, and then there's the base pointer and the stack pointer that point to the bottom and top of the current stack frame, which we're going to use a lot, and then the instruction pointer, EIP. The rest of these don't matter to us that much, but the EIP is very important. The EIP is where the processor records which instruction comes next. So if you gain the ability to change the EIP, you can take over control of the computer because you can point it to a different instruction to execute. And that's what we're going to do. We're going to find many various tricks that let us get control of the EIP, and that's how we take control of computers. So those are the general registers. There are segment registers that track sections of memory. We don't mess with them much. The main thing we care about is the instruction pointer and the stack pointers. Those are the ones we're going to use most. So they're all 32 bits in size in a 32-bit processor. And you can, by the way, refer to small pieces of the register. So EAX is 32 bits, but AX refers to the lower 16 bits, and AL to the lower 8 bits, and AH to these 8 bits. And this is for backward compatibility. You can run 16-bit code on a 32-bit processor, and you can refer to individual bytes. Now, normally you'd have no reason to do that, but we'll find out we have to do that when we start making shellcode, because remember this instruction back here, this simple example instruction that did a very simple thing that just put 42 in ECX. This instruction is all full of null bytes. It has 3 null bytes, and it turns out null bytes are evil. Null bytes break your exploit because you're typically inserting the data into a string, and the string is going through C. And C interprets a null byte as the end of a string. So if you try to inject something like this, it will only inject the 42 and the first null, and then it will ignore everything after that because it thinks it's the end of the string. So you have to rewrite your assembly code to avoid null bytes. And that's when you would use this old-fashioned trick of referring to just part of a byte, part of a word, like the 8 sections of it. Anyway, so those are the general registers, A, B, C, and D. You can use any of them for any purpose. There's a few conventions. A typically contains the return value. Couldn't you use little endian to avoid that? No, you can't, because whether it's a big endian or little endian, it would still have some nulls in it. Because the way strings are stored, and this is okay, so let's go back here. Okay, if you use big endian, it'd look like this, little endian would look like that. And in both cases, when strings are stored, you store 1 character in each byte. And so it would read a character here, and the next character would cause it to end the string. This way, any way you cut it, you'd have nulls. You can't have any null bytes, or to be more precise, you can only have 1 null byte, and it has to be right at the end of your string, because you can't have anything past the null byte. So the only way to avoid it is to not store a 32-bit value, but only store an 8-bit value. And that's why those instructions that refer to only 8 bits at a time turn out to be useful. Anyway, all right, then there are flags that keep track of status registers, like whether the last calculation ended up with 0 or a positive or negative number and such. And those are used for branch instructions, like jump if greater than 0, jump if equal to 0, that sort of thing. And I mentioned the most important thing to us is the instruction pointer. The instruction pointer is where it tells it what instruction to process next. And if I can change that, I can change what a program does. All right. So let's take a look at another Kahoot. Let me launch it here and then see if I can share it. All right. Now I go to my screen sharing and not that one, but this one. There we are. Yeah, that looks right. Good. It's a little more clumsy to switch screens, but I think it'll make a more readable video this way. All right. All right. All right, I'll give it a few more seconds. Aha, yep, looks like I better. All right. All right, so what kind of assembly language is malware typically written in? Forgot to mention it, but it's in the other class. You typically write 32-bit malware. It's the most common thing because it'll run on both 32 and 64-bit machines. You can write 64-bit malware, and more of that is coming out now that a lot of people have 64-bit machines. All right. So this is the loopback address. What kind of notation is that? It's big endian. This is the big part, the 127.0.0.1. Network addresses have to be interpreted in the big endian format. All right. And what are these things? Move and an XOR. Okay, they are called the mnemonic. That's the part of the command that is like a verb that tells it the action. Part of a machine language instruction. All right, an instruction puts data in EAX. What is EAX? Okay, that's a register. All right. And what is bracket EAX? Yeah, that's the memory address. Good. All right, let's see who the winners are. Sid, all right, I hope that's close to real name. If not, you'll have to give me more information to give your points to you. And RK, that may not be enough, might be initials. All right, if you might want to send me a chat message or something, tell me who you really are if you want to get your points. All right, and I saw, let me go back to the slides, which are here. All right, and I saw a question in there. Oh, good, I see MF telling me who he is, good. That one I could, that one was pretty close. Some of the others are a little more, but anyway, that's fine, good. Anyway, there's a question about if you can, how does it, the controlling the instruction pointer gives you control of the machine. And I see another student answering it there. If you're doing something like reading a book and I tell you what page to go to, I control what you see. And it's the same here. When you're processing a program, you're executing commands. And if I can change the pointer and move it to a different command, I then control what you do. Of course, I can only get you to do things that are somewhere in the list of commands that are already there. And we're going to talk about that later. Some exploits, I see Sid has told me who he is. Some of the exploits let you add new code, and other exploits only let you reuse code that the developer put there. But both of those are pretty powerful. All right. So let's talk about some of these instructions. So this move is the most common instruction. You move something from a source to a destination. This is called the Intel format with the destination first, by the way. So move ESP to EBP. In the AT&T format, it's the other way, move ESP to EBP. So I find this very annoying. You can look for these letters at the end, like long, that tell you the size of the instruction to figure it out. What I usually do is I look for a real number here. When I see an immediate value like this, that cannot be the destination. You can't put anything into 48. You can only put 48 into something. So find an instruction like that, and then you know which one of these you're using. But like I say, various things about this are kind of cruel. The Endianness is a problem, and the fact that there's two different ways to write a machine language, write assembly language, is also annoying. So it's pretty easy to get confused at first. So remember, indirect addressing, brackets mean that you don't go literally to this location. You interpret that data as an address and go to that location in RAM. So here's some examples. This puts EBX, whatever's in EBX is copied into EAX. This puts 42 into EAX. This goes to this memory location, 4037C4, and whatever 32-bit value is there goes into EAX. This takes EBX, interprets it as a memory location, goes to that location in memory, and whatever data is stored there goes into EAX. And this is one you'll see a lot when you're copying blocks of memory. You have EBX plus ESI times 4. So if ESI is incrementing through a loop, this will jump 4 bytes at a time, and it will copy the 32-bit words one at a time into EAX. All right. This shouldn't be the first one, be the other way around. Nope, you mean copy EAX into EBX? It might be more readable that way, but this is the way it is in the Intel format. Source to destination. All right. Anyway, load effective address is another one. This will calculate EBX plus 8 and put it in here. It'll put the address into here instead of the value, which is kind of annoying. Anyway, this would go to that location, EBX plus 8, find whatever was in that place in memory and put it in EAX. All right. And so here's an example from the book. You have EAX is 0, EBX contains this stuff. And if you go to that memory location, you see some data stored here. So EBX plus 8 refers to this word here that contains 20. All right, and so you can do all the arithmetic. You got increment and decrement, multiply, divide, subtract, and add. You got NOP. At first, this might seem pointless. NOP is the instruction that does nothing. So you might think it does nothing, but it turns out to be super important, just like 0 is important in mathematics. Now, the original reason NOP is there is because some instructions must start on a 32-bit word boundary. And as we saw, that move instruction we started with was 5 bytes long. So if you were to have that move instruction, and the next instruction has to start on a 32-bit boundary, you'd have 3 bytes you have to fill with something, and you'd fill them at NOPs. So that was the original purpose of NOP, just to pad, where you have to skip over a few bytes. But it turns out to be useful for hackers because we make a NOP sled. And that means if you have an exploit, and you inject it into memory, and then you try to run it, if you're wrong about the memory location, your exploit will fail. So instead of just putting an exploit in memory, you put like 1,000 NOPs before it. And now, if you miss the address by a little bit, you hit the NOPs, and the processor goes NOP, 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 and then runs your egg being the exploit you want. So very commonly, you will see a series of NOPs in exploit code. It makes your exploit more likely to work. Yeah, and copy, there is no real move instruction. The move command is really a copy command. It does not remove it from the other previous location, so that's important. They call it move, but it really would be probably better to call it copy. Yeah, just the original does remain. I see people talking about this. Good, very, very important to know. And then there's the stack. So you have ESP is the top of the current stack frame, and EBP is the bottom of the current stack frame. Push adds data to the stack and makes ESP get smaller, so the stack gets bigger, and pop takes data off the stack. And when you do a call to call a subroutine, that creates a new stack frame. And when you enter, we'll also do that. And when you leave or return is when you go out of a subroutine back to the calling routine, and that cleans off a stack frame. LEA calculates a value and puts it in there. It doesn't move any data at all. It doesn't copy or move. LEA calculates a value. LEA does, it puts a pointer. Yes, it puts a pointer to that location in EX. That's exactly what it does. Kara is correct. Good. These are very good questions going by in the chat. All right, so a small function program might do something like printf. When you enter a function, there is a prologue, which we'll see all the time at the start of a function that prepares the stack and makes a new stack frame so it can store the local variables. And at the end of a function, there's an epilogue, which will restore the stack and registers to their original values so the calling routine can pick up where it left off. And what we're going to do is exploit this process. We're going to corrupt it so that when it tries to return from a subroutine back to the calling routine, it gets confused and does something else instead. This is the point of vulnerability we're most commonly going to exploit. So it looks like this. You have your host system up here. You might launch, say, Microsoft Word. Then you might say, file open, and you open a open box. Then you're wandering through the box, clicking on something in some other subroutine. So you have the data for the Microsoft Word here, the data for the open box here, and the data, say you're typing into a file name field here. These are, that's what's going on here. These are stack frames. And when you call a stack frame, when you call a subroutine, it makes a new stack frame and goes in here. And when you return from a subroutine, it moves back here and stops using this data on the stack. So the stack frame contains all the local data you need on the stack. It has arguments that come in, then it has the local variables used by the stack, and then it stores the old base pointer and the return EIP on the stack. This is the fundamental weakness. So if I have something like a string variable in here, and it's got room for maybe 10 characters, and I'm able to put 100 characters in it, I can run past the end of the 10, and I can change this saved return address. So when it tries to return, it goes to a different address than it should go to. And that's what I've been talking about all along. This is how you get control of the EIP in a stack buffer overflow exploit, and that's how you take over the box. So you can test or compare things to see if they're equal. You can branch. JZ will jump if the last operation resulted in a 0. JNZ will jump if the last operation resulted in a non-zero value. And you also have jump greater than and jump less than, and so on. So in C, every program starts with a main method, and you've got arguments on the that go into the function. And so if I copy foo to bar, this has 3 words on the line. arg0 is copy, arg1 is foo, and arg2 is bar. All these lines can be referenced. All right. And so if you write simple C objects, you can spot them in assembly. EIP change in terms of stack. Well, if you go back here, here's the stack. Here's all the information of the subroutine you're in. You have local variables. When you are done and you hit return, it's going to try to return to this function, and it's going to resume execution at this location, the return address. If I was able to change that return address, it would not resume correctly. It would go run some other program. So this is why if you make a fuzzer and you send random data to a server, and you just fill this with garbage, it will crash. But if you very carefully choose the return address, you can gain control of the machine instead of making it crash. So that's how the stack is related to the EIP. And you'll see this all in much more detail as we go ahead in the projects. Anyway, sure. So here's a few common things you'll see in C. For example, here you have an integer, and then you add one with increment the integer. So an assembler, that would be define a word starting at 0. This makes a number, and this you could move the number into EAX, increment EAX, and then move the EAX back to the number. So it would take 3 assembly language instructions to do 1 line of C, incrementing 1 to the number. The return address has the function with malware. Well, yes, the return, you will have to find, if you want to take over the box, you will have to make the return address do something interesting to you. And therefore, typically you find some way to inject some code, which would be the malware, and you jump to the malware. Yeah, that's typically what you do. All right. So here's an if. You have a number. If number greater than 0, do something. So in assembler, you define a number. And here you would move it here. And an or will OR EAX with EAX. And the only point of that is that it will give you a 0 value if that will give you, this will give you 0, I think, if they're equal. And so the jumper greater than equal will jump down here, and otherwise it will execute this code. I always get a little confused at these steps, but that's the point. You have some kind of comparison, and then a jump greater than equal, jump less than equal here to create this if command. Like almost everything you do in C with one line turns into a few lines of assembler, and that's the point. That's why you make a high-level language, so it gets more done in one line and it's easier to read. So here you have an array of values, and then you set the third value to 9, because remember, they start counting at 0. So here you make an array with 4 zeros. Now you move EBX to 2, and here's array plus 2 bytes gets 9. So that's how it would look in C. You get used to spotting if you had 0 value index. No, these zeros are just immediate values to fill this array. The index is here, and it's in EBX. You had to put it in an array. And by the way, you might wonder why you don't just put a 2 directly here. And the answer is you only have certain instructions available. You have to look at the Intel reference manual and find out what commands are available. And in this case, you do not have the ability to offset by a fixed value, but only by a register. So you have to first put it in a register and then use the register as the offset. And here's a triangle where you're going to calculate something by multiplying area equals width times height. And I don't propose to go through all of it. I'm just pointing out here you have a multiplication, and there is an integer multiplication command. So that's all I want to put out here. You can so you can spot basically what goes on here. All right. And so that's all I wanted to do now. We're going to go through all this in much greater detail in the future. This is just the first chapter to get you started. This is what the exploit development handbook of ours interprets as what you should know before you start. And pop does not clear the stack. Pop removes one 32-bit word from the stack and changes the stack pointer. It doesn't clear the whole stack. It just removes one value. If you do many pops, then you'd clear more of the stack. Good. Very good questions. So let me go and do the last Kahoot, which is, I better launch it first. I figured this out. I launch it until I get the right window up. Okay, now I share that window, which is here. That should do it. Yeah, there we go. Yeah, it looks like we're right on track. Like I say, I like to only lecture for about an hour, and then I just answer questions. Although what I'm going to do after this is take a break, and then I'll demonstrate the first couple of projects to make sure you can all get going. I see from the names you may have a Republican on board. Logically, we ought to. Something like a quarter of Americans are Republicans, but they might just be a joke. However, I think we might very well have Trump again in 2024. The Republicans seem to still be very fond of him. I don't know what happens in CS 270. I can't answer your question, Shannon. But I don't think there are any security classes in CS, so it's probably not very similar. Anyway.
CS 270, I think, is the assembly class.
That's the assembly class. Yeah, I know they teach MIPS assembly, and several students have told me that that's a good class, and after that, they get more out of this class. So knowing some assembler helps them. Okay. But I don't think they do any security issues there. All right. No, there isn't a prereq. It's not an official prereq, but some people say taking assembly class first would help. Let's go through these. All right, the instructions at the start of a function. Okay, that's the prologue. Good. What mnemonic enters a function? Call and IC Kara taking assembly concurrently. That's a good idea, actually. That probably help. Yeah. All right, and what mnemonic multiplies two numbers? That's IMUL, that's integer multiplication. There are some floating point operations too, but we're not going to use any of them. All right. And what mnemonic compares two numbers? Okay, that's test. Good. And what mnemonic serves a special purpose for buffer overflows? Okay, that's NOPS. Like we say, it's used for the NOPS sled. And what mnemonic shrinks the stack? Yeah, that's pop. Remove something from the stack, and that makes it smaller. So let's see. Sid, good. Costas looks like a real name. And John Peck, that might be a real name too. Good. All right, I've got those recorded. All right, so I'm going to stop this recording and process it, and then I'm going to demonstrate some stuff. So it'll take about a 10-minute break.